In mathematics, profinite groups are topological groups that are in a certain sense assembled from finite groups. They share many properties with their finite quotients. A non-compact generalization of a profinite group is a locally profinite group. Definition: a profinite group is a topological group that is isomorphic to the inverse limit of an inverse system of discrete finite groups. More formally, a profinite group is a Hausdorff, compact, and totally disconnected topological group. That is, a topological group that is also a stoned space. In categorical terms, this is a special case of a filtered limit construction. Examples: finite groups are profinite, if given the discrete topology. The group of p-adic integers Zp under addition is profinite. It is the inverse limit of the finite groups Zp and Z, where n ranges over all natural numbers and the natural maps Zp and Z, Zp and Z are used for the limit process. The topology on this profinite group is the same as the topology arising from the p-adic valuation on Zp. The Galois theory of field extensions of infinite degree gives rise naturally to Galois groups that are profinite. Specifically, if Lk is a Galois extension, we consider the group G equals Gal consisting of all field automorphisms of L which keep all elements of K fixed. This group is the inverse limit of the finite groups Gal, where F ranges over all intermediate fields such that Fk is a finite Galois extension. For the limit process we use the restriction homomorphisms Gal-Gal, where F2, F1. The topology we obtain on Gal is known as the Kroll topology after Wolfgang Kroll. Waterhouse showed that every profinite group is isomorphic to one arising from the Galois theory of some field K, but one cannot control which field K will be in this case. In fact, for many fields K, one does not know in general precisely which finite groups occur as Galois groups over K. This is the inverse Galois problem for a field K. Not every profinite group occurs as an absolute Galois group of a field. The fundamental groups considered in algebraic geometry are also profinite groups. Roughly speaking, because the algebra can only see finite coverings of an algebraic variety. The fundamental groups of algebraic topology, however, are in general not profinite. The automorphism group of a locally finite-rooted tree is profinite. Properties and facts. Every product of profinite groups is profinite. The topology arising from the profiniteness agrees with the product topology. The inverse limit of an inverse system of profinite groups with continuous transition maps is profinite, and the inverse limit functor is exact on the category of profinite groups. Further, being profinite is an extension property. Every closed subgroup of a profinite group is itself profinite. The topology arising from the profiniteness agrees with the subspace topology. If N is a closed normal subgroup of a profinite group G, then the factor group G, N is profinite. The topology arising from the profiniteness agrees with the quotient topology. Since every profinite group G is compact Hausdorff, we have a Haar measure on G, which allows us to measure the size of subsets of G, compute certain probabilities, and integrate functions on G. A subgroup of a profinite group is open if and only if it is closed and has finite index, according to a theorem of Nikolai Nikolov and Dan Siegel. In any topologically finitely generated profinite group, the subgroups of finite index are open. This generalizes an earlier analogous result of Jean-Pierre Serre for topologically finitely generated Pro-P groups. The proof uses the classification of finite simple groups. As an easy corollary of the Nikolov-Siegel result above, any surjective discrete group homomorphism phi GH between profinite groups G and H is continuous as long as G is topologically finitely generated. Indeed, any open subgroup of H is of finite index, so its pre-image in G is also of finite index, hence it must be open. Suppose G and H are topologically finitely generated profinite groups which are isomorphic as discrete groups by an isomorphism iota. Then iota is bijective and continuous by the above result. Furthermore, iota -1 is also continuous, so iota is a homeomorphism. Therefore, the topology on a topologically finitely generated Profinet group is uniquely determined by its algebraic structure. Profinet completion. Given an arbitrary group G, there is a related Profinet group G caret, the Profinet completion of G. It is defined as the inverse limit of the groups G, n, where n runs through the normal subgroups in G of finite index. There is a natural homomorphism eta, G caret, and the image of G under this homomorphism is dense in G caret. The homomorphism eta is injective if and only if the group G is residually finite. The homomorphism eta is characterized by the following universal property. Given any Profinet group H and any group homomorphism F, GH, there exists a unique continuous group homomorphism G caret H with F equals G eta, IND finite groups. There is a notion of IND finite group, which is the concept dual to Profinet groups, i.e., a group G is IND finite if it is the direct limit of an inductive system of finite groups. The usual terminology is different. A group G is called locally finite if every finitely generated subgroup is finite. This is equivalent, in fact, to being IND finite. By applying Pontryagin duality, one can see that abelian Profinet groups are in duality with locally finite discrete abelian groups. The latter are just the abelian torsion groups. Projective Profinet groups. A Profinet group is projective if it has the lifting property for every extension. This is equivalent to saying that G is projective if for every surjective morphism from a Profinet HG there is a section GH. Projectivity for a Profinet group G is equivalent to either of the two properties. The cohomological dimension CD1. For every prime P the SOLO P subgroups are G are free pro P groups. Every projective Profinet group can be realized as an absolute Galois group of a pseudo-algebraically closed field. This result is due to Alexander Lubotsky and Lou van den Dries.